In this video, I'll cover how to do an unsteady state mass balance specifically on a water storage tank. This example is given in your textbook, example 10.2-1. It says a 12.5 meter cube tank is being filled with water at a volumetric flow rate. At a moment when the tank contains 1.2 meters cube of water, a leak develops in the bottom of the tank and gets progressively worse with time. The rate of leakage can be approximated as this, where time is the time from the moment the leak begins. Couple things. I've underlined the values that are given in the problem statement, and the book actually goes through and it gives you a process flow diagram here, where the things I was underlining are the things I'm picking out of the problem. So the volume, overall volume of the tank is 12.5 meters. Important to note that the volume of the tank is not necessarily the same as the volume of water within the tank, because obviously, unless the tank is full or overfilling, the volume of water will be less than the overall volume of the tank. And it should be. If the volume of the water meets or exceeds the volume of the tank, then we could have a spill, and that's a problem. So usually when it says the volume of the tank, this is superfluous information, and I don't actually need to know that unless I am concerned with calculating a time at which the tank overflows or something. So I'm not going to exit out. I'm just going to note that oftentimes when we're doing balances like this, we're going to be balancing the water inside the storage tank, not actually the volume of the tank itself. Another way to think about this, as the volume of the water rises, or as the water level rises or falls, the volume of the water will change. That part is unsteady. The volume of the tank is steady. It's a rigid tank, I'm assuming, so there's no change in volume for the tank. Okay, I have an inlet flow rate of 0.05 meters cubed per second. Important to note that this value is a constant. In other words, it is not a function of time. Right, so I have to be aware of which things are constant and which things are changing with time. So let me just make my notes in blue here. I'll exit out over here as irrelevant. Again, unless I wanted to be concerned with whether or not the tank overflows. The outlet flow rate is a function of time because it has a t in it. Right, so this is a function of time, so I have to be aware of that. And there was one more rate given. Oh, at a moment when the tank contains 0.2 meters cubed of water, a leak develops in the tank. So this is an initial condition. So it doesn't really mention where or what time. I think it does actually. Yeah, t in seconds is the time from which the moment the leak begins. So this is my initial condition. That's given here. So these are the things I'm looking for when I start the problem. First of all, you'll always need to have some initial condition or boundary condition. You'll have to know what the value is for any specific value of the independent variable. You also probably want to know what the inlet and outlet flow rates and what the generation and consumption rates are, but not for a mass problem, right? For a mass problem, mass is conserved, so there is no generation or consumption. Later when we do reactions, we'll be concerned with generation or consumption. All right, part 1 says to write a mass balance on the tank and use it to obtain an expression for dV dt. Okay, notice that it says write a mass balance on the tank, but then it says obtain an expression for dV dt. So this would be a volume balance. All right, so I have to be careful of differentiating that in my head. So I am always going to recommend starting every problem with a mass balance because we know it is conserved. Volume is not necessarily conserved, as we've seen several times over the course of the semester. If temperature changes, if pressure changes, if you're mixing two chemicals where the delta V mix is non-zero, that's going to change the volume. Volume is a very fickle process variable. So you always want to start with either a mass or a mole balance. But here for water, it's easier just to do a mass balance. So mass balances are of the form in minus out is equal to accumulation. Of course, I've already canceled generation and consumption. So my rate of mass flowing into the tank is given as 0.05. Oh, actually, wait a minute, it's not. That's the volumetric flow rate, right? I want to write these things in algebra terms first. I'm going to call it M in minus M out is equal to dm dt. All right, that's the first step. I don't want to immediately jump to putting variable names in there. Now, as I almost did, right, I almost put the volumetric flow rate in for the mass flow rate. So how can I relate using the principles of what I've known so far throughout the entire semester? How can I relate the volumetric flow rate to the mass flow rate? Well, I know that the mass of anything is the density times the volume, right? So for all of these terms, I can, instead of writing mass, I can instead write density. So I can write rho times v dot in minus rho times v dot out is equal to d rho v dt. And then I can say that because water is an incompressible fluid, incompressible liquid to be more precise, and there's no huge temperature changes, there's no pressure changes, but even if there were, the fact that it's incompressible means that the density is constant. I can now factor this density outside of the derivative, as I showed you in the calculus refresher video, and then I have a common density that can be canceled because it's constant. And therefore, if I simplify the mass balance a little bit more, I get dv dt is equal to v in minus v out. All right, and that was the thing that it asked me to do, obtain an expression for dv dt where v is the volume of water in the tank at any time. All right, that is done. Provide an initial condition for the differential equation. Well, that is given. So v of times 0 is equal to 1.2 meters cubed. Okay, solve the balance equation to obtain an expression for v of t and draw a plot of v versus t. Okay, in order to do that, all we have to do is plug in our values for v in and v out, which are given in the problem statement. So I have dv dt is equal to 0.50 minus 0.0025t. Okay, I have a separable differential equation. I can take the dt over to the other side and integrate. So integral of dv is equal to integral of 0.50 minus 0.0025t dt. So v is equal to 0.50t minus, let's see, 1/2 of this is 0.00125 t squared plus c. Now I can plug in my initial condition, which is that at time is equal to 0. So on my right-hand side, time equals 0 is going to cancel out both those terms. So I get c is equal to 1.2. And therefore, my final expression for v of t is equal to 0.50t minus 0.00125 t squared plus 1.2. Now, if I wanted to plot this more formally, I could go to Excel, and for all values of time, I could simply take t and calculate my value of v of t. So for a time of 0, I already know that my v of t is going to be 1.2. And I could choose different values of t, and I could calculate my value of v of t. I just want to do a more qualitative analysis here. So plotting v as a function of time. So I know that at time is equal to 0, I'm going to start at 1.2, and I haven't really thought much about my scale here. What is the plot going to look like? So at time is equal to 0, how should I start drawing this graph if I don't want to go to Excel and start drawing things? Well, remember from calculus that dv dt you can think of as the slope of the curve at any particular time t. So for instance, at t is equal to 0, my slope dv dt is equal to 0.5. So my first initial slope is going to be up and to the right. But as I continue moving, through time, right, this second term, I pick a different color to highlight it, is going to keep increasing. And as this second term keeps increasing, because it's negative, that means the overall slope is going to become less and less positive as we go. I'm going to plot this in light blue, I think. So it's going to start off at 0.5 and slowly it's going to start kind of leveling off until a point where it reaches 0. And you can tell what point that is by taking the derivative and setting it equal to 0. So let's do that. So at, let's see, what time is this going to be? So 0 is equal to 0.5 minus. So I'm looking for the point at which the slope is equal to 0. That's going to be my maximum, remember, from calculus. This is an application of why knowing what the maximum is useful, very useful. That was a slip of the tongue. And I've just realized I've been writing this wrong the entire time. This is 0.05 as given in the book. So just let me fix all these. 0.05, 0.5, 0.50. So solve for t. Equals 20. So the point where the derivative is 0 is going to be the local maximum of my function. That is going to occur at 20 seconds. And then after that, my flow rate is going to start becoming negative again. All right, and it's going to keep going negative until it reaches 0, but practically we know that you can't have less than 0 water in the tank. So this is again another example of why it's important to be an engineer and not a calculator. You know that at a certain time, there's not going to be any water left in the tank, and I can't drain water out if it doesn't actually exist. So this is what the graph would look like. You could also calculate at what time that occurs. That's another useful thing that would be useful to know. So when will the tank be empty? So in order to answer that question, you have to answer the question, where or at what time will V of t be equal to 0? So you can take this equation that you've derived, 0 is equal to 0.05 t minus 0.00125 t squared plus 1.2. Solve for t from the book, that's 57 seconds. I'm kind of skipping around a little bit, but another useful question you can ask yourself is, will the tank overflow? So at the very beginning, I mentioned that that's one thing you might definitely want to know. If the whole tank is 12.5 meters, you could ask yourself at any point, will the volume exceed 12.5 meters cubed? So in order to do that, you can calculate what is the maximum volume in the tank. Is the max V in the tank. As a side question, will it overflow, and if so, when? And how you do that is you take the derivative, and because we solved the differential equation, we already had the derivative. And set equal to 0. Now this also works for finding the minimum. So you have to do a little bit more analysis and be aware of whether or not you're calculating the maximum or the minimum. Okay, so that's all for this example. We'll get into some more examples in the next couple of class periods.